Okay, getting this recorded. And if you're watching this at some later time, I'm going to, for this recording, I'm just sharing the screen because I think maybe that way you'll at least get to see what's on the slides. And then if I write something down, I'm just going to describe it. And maybe you, if you watch it later, you can get notes from someone in the class. So first I wanted to see, do you all have any questions about unknowns stuff? Okay, so whenever, I don't know who is the last faculty to leave today, but whenever the lab gets closed today, like that's pretty much it. So everybody had enough materials and so on.
Just making sure we only do the report on one of them.
Yeah, you just do a report on one. So if you need, your report needs to say what the other one was, but you don't have to talk about how you figured it out. So I would advise you that whichever strain you're the more sure about, make your report about that. And if you're very sure about both of them, you can just decide which one of these would be easier to write about. So when you submit those on Canvas, I will take a look and then go ahead and put in the grade for did you get them right? And then the reports, my goal is to have your reports graded by Thursday, November 30th. Because then I have got another set of papers coming at me to grade. So that's my goal. The second announcement I wanted to make is that I was looking on Canvas at older videos that I have from past semesters, and there was one that I made last year that most of the video is me talking about the final and what's on the final and how to study for the final, and that's still very relevant to this year's final. So I have made that available in Canvas, and it says something like, I forget what I called the video, but it's basically talking about what the final is going to be. So if you would like a preview of that, somebody had asked me what's going to be on the final. Take a look at that video, and it's kind of long, but it's telling you what's going to be on this year's final as well. So hello, I feel like we're going to have the attendance award for percentage of people attending on the class the day before Thanksgiving. I'm thrilled. Good job. So any other questions that you have before break? Or? Okay, well, we'll keep talking about chemical control methods and finish that up. So last time when we had been talking about the chemical control methods, I mentioned one called gas sterilization that used ethylene oxide. And I think you all have a lot of notes written down about ethylene oxide, but I wanted to talk a little bit about this equipment and an example of when you would need to use this. So this is an endoscope. And an endoscope is put down through someone's mouth, down the back of their throat, down their esophagus, and usually into their stomach at least, and possibly on into the beginning of their small intestine. A similar process could occur like during a colonoscopy going from the other direction. So it's a camera that lets doctors look inside the digestive tract. And these are very advanced. They've got a lot of plastic, they've got electronics, and they're going into some very contaminated parts of the body. So endoscopes are an example of something that would get gas sterilized. And about 10 years ago, there was an incident in California where someone didn't sterilize it correctly and then reused those endoscopes on new patients, and they were getting infections that turned very bad. So this is an important, this sterilizing method, and it's important that it be done correctly. Drawbacks of this are that it's expensive. Like, the average person could not do gas sterilization. It's expensive, it's very technical. The gas is very toxic. But this is one of the best way to preserve, delicate machinery. You don't want to heat it, you don't want to put it in liquid, you don't want to scrub it with tiny brushes. Do gas sterilization. It does sterilize. So do you have your star of sterilization? Yeah, good. And then we have two more methods for the chemical methods, and one of them, these are both really old school. So we go from the most modern, the most expensive, the most strange to the basic and old school. And that is to use a category of chemicals that includes soaps, surfactants, and detergents. Soaps, surfactants, detergents. And all of these molecules have in common that these have amphiphilic chemical properties. Amphiphilic, AMPHIPHILIC. And if a molecule is amphiphilic, I'm drawing a picture of these little green shovel shaped things. They're going to have a hydrophilic, and hydrophobic end. A water loving end and a water hating end. So what I just drew is a thing like this shovel looking thing here. And this section is hydrophilic. This section is hydrophobic. So you can see that those molecules can get into a membrane and kind of wedge themselves in there, and they're going to break up a cell membrane. And this is also why we use soaps to dissolve grease. Same chemical property. So these as a group will break up cell membranes. That's one of their actions. And their second action is to just help remove dirt and debris. So really useful for getting crud off of surfaces, whether that's your hands or a countertop or a floor. They all act the same way. They do not sterilize. They can disinfect. They can do antisepsis if we're using soap on a body surface, but they're a good bang for your buck. They are going to reduce microbes wherever you use them. We'll add a note. They do not sterilize. But you can imagine, say that you have surgical tools that need to be processed for sterilization. You might first wash them with detergents, and then where their aldehydes go. Then you might soak the tools in glutaraldehyde and get them sterile. So sometimes these methods are used in combination with each other. And then finally, we go to another very old school method of preventing contamination or killing microbes, and that's to use metals. So metals in high concentration will either inhibit microbial growth or, depending on the metal and how much of it there is, it can kill microbes just by exposure to metal. So examples are silver, mercury, zinc, tin, gold, and probably some others. And I found this kind of cool to think about. I had not thought about this, but in olden days, when the king drinks out of a silver chalice, like is on the screen, it's disinfecting what he drinks, which is cool. When you get tooth fillings, if you get the old school style that's metal, the filling itself will suppress microbial growth around it. And if you have old school bronze doorknobs, they inhibit microbial growth. So whenever I have students swab a doorknob, it's usually hardly anything grows there because the metal is inhibited. So ways that this will affect you guys is if you ever put copper, like copper sulfate drops, or there's drops that go in infant newborns' eyes that prevent infection, and they have silver in them. That's a metal-based inhibition, which is also cool. So those are our chemical methods for microbial control. And I'm gonna go back to this picture that you all don't actually have, but just use it for describing something. So on the chemical agents that I talked about just now, most of them are liquids. So out of that list of 8, I think you had 6 that are technically a liquid, 1 that's a gas, and then metals, which can be dissolved or a solid chunk of metal. And you'll want to know out of those types, the following things. So which ones of them sterilize? Metals do not, by the way. Metals don't sterilize. And which ones of them sometimes get used for antisepsis, like on people? So I think maybe we should quickly go back and talk about the antisepsis ones. So iodine, which is a halogen, that could be used for antisepsis on a person. Or betadine. Does anybody know how to say it? I just read it on the bottle. Phenolics, we don't really use those on people. Alcohols, yes. We use those for antisepsis. Peroxide, yes. Aldehydes, no. Not used on people. Not living people. No, definitely not. Not gas sterilization. That's not for antisepsis. Soaps, yes. And metals, maybe. Maybe. Okay, so we're next going to switch our slide set and get started talking about antimicrobial drugs. And one celebration here, this is the last slide set for the semester. So we use it today, and then we'll use it after Thanksgiving as well. And this is talking about drugs. So the beginning of, we say that the beginning of humans using antimicrobial drugs started with Alexander Fleming. He maybe was not the first person to do this type of work, but was one of the first to write it down. So this gentleman is Alexander, spelled the usual way, Fleming. Fleming. And he was working with bacteria, and he started some on a plate. And he was trying to grow bacterial colonies on a plate. So I'm drawing a picture of this on the board. And I think he went on vacation or went to somewhere, and then he came back a while later, and he discovered that on the plate there was a big fuzzy fungus on some of the plates. And around the fungus, he noticed that wherever the fungus was, there was a big ring around it where no bacteria would grow. But the bacteria were growing other places on the plate that weren't close to the fungus. And if you're watching this on the video, you'll want to get this picture from a friend. So if that were me, I would be like, dang it, contaminated plate, and I would throw it away. I would, go on about my business. But he noticed, and he thought about what it meant that around the fungus, there were no bacteria growing. And he realized maybe the fungus is making something that's leaking out of it, that's killing bacteria and causing that dead zone around itself. And now that we've been through microlab, we can kind of recall, like, oh, that's kind of like those drug disc tests that we did, and it's a similar thing. So he noticed it, he thought about it, and then he started working on that problem. And what he was working on is figure out what is leaking out of the fungus and try to research it. And as a result of that, we say that he discovered penicillin. So what it turned out to be was the compound that we now know as penicillin. We should not say that he invented penicillin. It's actually a natural product that's made by fungus, but he worked on identifying it and helping it get commercially produced. And this was happening in between World War I and World War II. And by the time of World War II, penicillin was being mass produced, and it saved a lot of people's lives, of soldiers who got wounded. And in World War II, if you got wounded and got infected, you might recover. In World War I, if you got wounded and got infected, probably the infection would kill you, even if the wound could have healed. So this was world changing. Just in time, 1944, mass production of penicillin. And I want to show you guys too. This is his lab, and we can see plates, and they were glass back in his day. Somebody had to wash them. It's usually women had to wash them. And then behind him, these are his test tubes, and the test tubes don't have caps, they have cotton wads in the top. And that kept the microbes out. So interesting. Okay, so that was the beginning of people working intensively with antimicrobial drugs. And if we had a perfect antimicrobial drug, we would want it to kill the microbe but do nothing to us. So out to the side here, you could write low side effects or no side effects. So we hope that it has no side effects. Secondly, we hope that it kills microbes and doesn't just slow them down. We want it to be microbicidal. And then these two, I'm going to combine them together because they relate to each other. So we hope that the drug will work well in a person and dissolve in their body fluids. That's actually not always the case, but we hope it's soluble. We hope it works in a high dilution, and we hope it stays in the body long enough to do some good. So those two I want to combine and write a note about that. So those two things together, if they were true, you could use a very small dose infrequently. So if it dissolves really well and it stays active, and you don't break it down fast, those will be your type of drugs that it's a really like a small pill once a day. If you've ever been on an antimicrobial drug that you had to take big pills 4 times a day, it's probably because you're peeing out the drug too fast. So you got to keep taking more. Let's see. These two, I don't have anything to say about it. This one's related to these two, remains active. We hope that it can get to where the infection is. And that one delivered to the infection site. That's going to relate to, is this an IV drug? Like, do we have to give it through IV? Is it topical? What's that mean?
Skin.
Like you're putting it on the outside of yourself, like a cream or a spray or something. Topical. Or is it oral? Is it pill form? And we hope that it's cheap, and we hope that it's not going to make people allergic. Most drugs don't have all of that. They usually have some characteristic, but not all. But this, if there were perfect ones, they would have all of these characteristics. So we have here some definitions of what do these different terms actually mean in regards to antimicrobial drugs. So the first one that I want to start with is antibiotic. Because that's what a lot of people know or think they know that word, and that's maybe the most familiar term on here, but what it actually means is maybe not what people think it means. If you're watching this online, maybe get this definition list when you get back to town from a classmate, because we're going to write some definitions on the board. So, definition of antibiotic is something that is made in nature. Let's call it, let's say, a chemical that is made in nature. That blocks some microbes. So an antibiotic, it's a naturally occurring product, like made by a fungus or made by a bacterium that blocks some microbes from growing. Our second definition is antimicrobials. So an antimicrobial is any chemical, whether it's made in nature or not, that blocks microbes from growing. So that's our broadest type of term, antimicrobials. If it's antibiotic, it's something that was made in nature. So we could include within antimicrobials, antibiotics. That's a subcategory. Okay. I also want to put under the category of antimicrobials some terms that aren't up here yet. So within these, we could include antibacterial drugs, which are specifically against bacteria. We could include antiviral drugs, antifungal drugs, antiprotozoan drugs, and antihelminthic. So there are different ones for each category of microbe that infect us. Some drugs are both antibacterial and they have a natural origin. So they would be both antibiotic and antibacterial. So this one is about, is it lab made or naturally occurring antibiotics? Next definition that we have up here is a semi-synthetic. So a semi-synthetic drug they're going to start with a natural product, but they're modified in a lab. They would be also a type of antimicrobial. We can also have a category of drugs called synthetic or full synthetic. So a synthetic drug is completely constructed in a lab, like a chemistry lab. You don't start with a natural product, you just do chemistry from scratch, let's say. And then the last one I want to talk about before I move on to narrow and broad spectrum is the concept of a prophylactic or prophylaxis. Prophylaxis means prevention. So there are some, long time ago, people didn't like to say the word condom and they just called them prophylactics. condom's way easier to say. It's a thing to do prevention. So prophylaxis just means to prevent something, but a prophylactic drug is to prevent a condition or a infection. Sometimes people that, I was reading this article about a girl in the Peace Corps that got malaria, and her family was suing the Peace Corps because they didn't give her appropriate medical care. So she wasn't taking her anti-malarial pills like she was supposed to. So if you're in a high malaria area, there are drugs that you can take to prevent getting malaria, and she was not doing that. And they should have been ensuring that she was. And then when she got malaria, she also got terrible medical care. And she died, and it was very sad. But I thought, man, why wasn't she taking her? Why weren't you taking your anti-malaria drugs? That's important. That would be an example of prophylactic drug. Okay, so next, couple of other definitions that we want to use have to do with how many types of microbes will that drug actually work against. Is it a lot or is it just a few? And we call this their spectrum of activity. Narrow spectrum, broad spectrum. So we've got here an example of some different drugs. So these names underneath the colorful bars, those are categories of drugs like penicillins. And up on top here, we have categories of bacteria. So these are all bacteria, and these are the different families of bacteria that tend to cause people medical issues. So we've talked about gram negatives and gram positives. And then there are some weirdo groups that are neither, like chlamydia, like rickettsia and mycobacteria. So penicillins, we can see that it's good against gram positives. Generally, it'll cover that group. It will prevent them from growing. A little bit of the chlamydia group and a little bit of the gram negatives. But they would do nothing against mycobacteria and some of the gram negatives. This group has a very far extending range of effectiveness. So we would say that tetracyclines are a broad spectrum drug. So let's start with definition of broad spectrum. A broad spectrum drug is going to be effective against a large variety of microbial groups. Change this to bacterial groups. Usually we use these for the antibacterial drugs. And conversely, a narrow spectrum drug is only going to be effective against a few bacterial groups. What seems to be a very narrow spectrum drug up there? What'd you call it? Polymyxin? Mm-hmm. Polymyxin just treats a few types of gram negatives, and tobramycin, a very few gram negatives and some of the mycobacteria. So those would be narrow spectrum. These drugs have broad versus narrow spectrum. They have advantages and disadvantages. So for the broad spectrum, if you don't know what is infecting a person, broad spectrum are more likely to work. So that can be an advantage. If you don't know what's infecting someone, you might want to try a broad spectrum antibiotic. But drawback of that, what would be the drawback of broad spectrum?
Other side of this.
They will have more side effects. Like
It's
what?
not gonna be as strong. Like to kill that certain thing.
They can be pretty strong. And they used to be way more popular than now, but their big drawback is that because they're so broad spectrum, they're likely to kill our beneficial microbes. And that's a big negative. So if you remember back to that video about the woman that needed the fecal transplant, her problem started from taking a lot of antibiotics of different types for a long time, and basically it killed all of her normal gut flora, and she had a hard time getting over that. So in recent years, the medical community is moving away from broad spectrum if possible. Narrow spectrum will preserve more of our beneficial microbes. So that's a benefit, but the drawback is that before you prescribe a narrow spectrum, you need to have some idea of what's infecting the person. Or have an educated guess at least. When I was, first time I went to Malaysia with Han, I got such bad food poisoning from the chicken. Did I tell you all that story? Chicken. I didn't like much of the food, and we went to this cookout where somebody was grilling chicken and peanut sauce, and I really liked that. Like, finally. Something that I like to eat, and I ate a lot of it. But it was dark, and there was a sauce on the chicken that covered up the taste of rawness, and it wasn't cooked all the way. And it also had been marinating in that stuff for like a long time in the trunk of someone's car, I think. I got so sick from it, and I was distrustful of Malaysian medical care, which is ridiculous. They have really good medical care. So I just suffered with that the whole rest of the trip, and then came home on the airplane and bombed the airplane toilet multiple times on that long flight, and got back to the good American healthcare, I thought. Went to my school's clinic. And I told them where I'd been and all that, and they said, we need to have a stool sample to figure out what you have. And I was so upset. Just in my mind, I thought, but I get the sample, and they like did 3 days to test it, and I was still having a lot of problems during that time. And then they said, we don't know what it is. You should use some Z-Packs. Broad spectrum. And it fixed me for the time being. But that was a major, in Indiana University, and they're using the best healthcare standard of care, because they have a major research hospital associated, and they were doing it right, but it felt bad to me. no, I need something today, right now. I want to stop. Pooping my guts out. They were trying to do the right thing for me. And I guess in the end they did. But that was the worst food poisoning. So we know that narrow spectrum are preferred if we know, or we think we know, what's causing the infection. Because we don't want to mess up our good bacteria. And if we can preserve our good bacteria, we'll be less likely to get what's called a super infection. And this is a new definition to us also, a super infection. So super infections are going to occur when a normal microbe in the body overgrows. Like it's over dominating the mixture of microbes that you have in your gut, let's say, or it could be on the surface of your skin. So you're supposed to have a healthy balance of microbial types. And if you do have a healthy balance of types, maybe a microbe that was there and is not a pathogen yet, if it happens to survive the broad spectrum drug and all the other ones are gone, now that one has a clear field to just overgrow. And we call that a super infection. Super infection is an example of a secondary infection. So there was a first infection and we prescribe a drug to fix that. And then that drug caused this problem. And now the person has a secondary infection with this other thing. So super infections are a type of secondary infection. So super infections can be C. diff or Clostridium difficile. Any type of yeast infection in the body is usually a super infection. You already have the yeast, but you're on antibiotics and you kill a lot of stuff that's not yeast, and then the yeast goes crazy. Cause, thrush or vaginal yeast infection or skin yeast infection or something like that. So those are both super infection. So since the days of Alexander Fleming, right after that, there was so much excitement and marvel at how useful antimicrobial drugs were to prevent people from dying and to help them, recover better from infections. There was a ton of research activity. Let's make new antimicrobial drugs. And we have a lot of kinds now. All of the different kinds of antimicrobial drugs are targeting something in a microbe to damage it. So these are the targets of drug action, and there are 5. Some of them overlap with the targets of chemical action. So we've got cell wall, that's type 1. I guess I could just write the numbers on it. So type 1 we'll call cell wall blockers. Type 2, plasma membrane disruptors. Type 3 are ribosome blockers. Type 4 block DNA and RNA synthesis. And then the fifth type are a little bit more, there's fewer of them, and the fifth type are ones that block a very specific process in the cell that doesn't fit into one of these other categories. Those are the targets. So when we started off this unit with talking about the eukaryotic parasites, and I went through and talked about what they do and they don't have, that relates to the drug treatment. So if someone is infected with a fungus, they need to use a drug that will do something to a fungus. If someone is infected with a bacterium, they need to use a drug that will do something to a bacterium. So out of this group, there are, let's kind of list, how to say this. I don't know how to describe this. Let's list down, okay, here are the types of microbes that infect us. So we've got bacteria, viruses, fungi, protozoans, and what's the last one? Helminths. Yeah. Bacteria, viruses, fungi, protozoans, helminths. And bacteria are very structurally different from us. So there are lots of non-shared targets with bacteria. So there are lots of drugs available. There are a lot of drugs that work well against bacteria, a lot of choices. Because they have so many targets that we don't share. Viruses have very few unique targets. So there are few unique drugs that will work against them. And that's true for these other groups also. So viruses don't have many unique targets because they're mostly using our stuff to damage our body. So how do you pick out a target that will only affect the virus and not mess up your cell? That's difficult. There's not many great antiviral drugs. And then the fungi, the prokaryotes, the protozoans, and the helminths. Love that happens. I don't know. I know it came from somewhere over here, but they're eukaryotes, and we're eukaryotes. So finding a drug that will harm them and leave us alone is also not easy. So on this screen, most of the drugs on this screen are bacterial fighting drugs. And I don't have you all learn in this class, like which ones are for bacteria, which ones are for viruses. And have to learn a lot about their drug names because I think you'll get that knowledge at the level that you need in nursing school. Now, if you have friends that are going to pharmacy school, they have to know all of it. Every drug, every target, every pronunciation, every dose, all of it. But these are, you know, a good overview of it. And there's one category that I do want to focus on, which are the penicillins. And we're just going to use that as an example of how a drug works and what modifications can be made to it. So penicillin is a cell wall blocker, and this one we are going to write literally what it does. I'm making sure that I don't. Oh yeah, I do have a slide about this, so we'll write it on here. So penicillins are cell wall blockers, and what they literally do, any drug that is penicillin or a derivative, just call it penicillin drugs. They are going to block the building or the repairing of peptidoglycan. So for a cell that is not dividing, if you expose it to penicillin, it won't die right away, but it won't be able to fix problems that eventually happen in its cell wall. So eventually its walls would fall apart. And if it were going to try to divide and it would have to build new cell wall before dividing, it can't do that. So it's basically microbistatic more than microbicidal, but it doesn't matter too much in the end. All penicillins and everything in this slide and this table are penicillin types. So here's the OG original penicillin that Alexander Fleming discovered, this one right here. And the key chemical part of a penicillin is this particular stuff highlighted in blue. It's called beta-lactam ring. And having a square like that is kind of odd in chemistry. It's kind of special. So drugs that have this are called beta-lactam drugs, and that's your penicillin-based drugs. And they all have that. So when we look at the version of penicillin, we're going to start with the original one, which is called penicillin G. And penicillin G works pretty well on gram positives, but not that many gram negatives. Why would gram negatives not be as susceptible to a peptidoglycan blocking drug?
Okay.
They have thin peptidoglycan and they've got that membrane around them that kind of protects them a little bit from this drug. So the original penicillin was not super broad spectrum, and I'm circling this word parenteral administration. Y'all learned that somewhere before? Med term? No? This means that you can't take it in a pill. It's got to be a shot, something not oral. So the original worked pretty well against gram positives, and it had to be given in a shot. And this is an antibiotic. It's completely natural source. But then using the power of chemistry, all of these other versions of penicillin were eventually developed as semi-synthetics. So on this chart, this one is antibiotic. All of these and the ones that came after it are semi-synthetics. I think these ones up here are also semi-synthetics. So taking penicillin as the starting material and do chemistry on them in the lab and improve them. So the first innovation in penicillin was to change it so that it could be made into a pill. That's great. Penicillin V has chemical modifications that you can take a pill and there's enough of the drug that survives your stomach acid that it will get into your blood that way. So that was an improvement. And then the next improvement was to make ampicillin, which is a little bit more broad spectrum. So slightly broader spectrum. And then there was amoxicillin. And how many of you had constant ear infections when you were a child? My mom said, I thought that you were about to go deaf. I had ear tubes and that fixed my problem. But until I had ear tubes, I must have drunk 3 gallons of that pink antibiotic amoxicillin. They made it like taste like bubble gum. And like we always had a thing of that in the fridge, and I had to have so much of it. There you go. Amoxicillin. And it would beat back my ear infections for a while, but ear tubes eventually fixed my problem, as well as just growing pollen. So did you know when you're a little kid, your ear tubes connecting to your sinuses and your ears, they're flat. And as you grow, they become slanted so that you get better drainage and don't keep bacteria in there as much. That's why little kids get ear infections so bad. Flat tubes, slanted tubes. Cool. Growing up is good. Hearing is good. And then this one out here on the end, methicillin. I want to say a little bit about that too. This is one of the newer types of penicillin semisynthetics. It's new-ish, say like in the last 30 years. It's a newish advance in penicillin. And it's designed to designed for drug-resistant infections. Methicillin. So notice out here, it's good for gram-positives, including beta-lactamase producers, and it's parenteral. So how would people have to get this drug? Shot or IV? Methicillin. It's the newfangled version. Oh, you are such patient people. That's the perfect place to stop. So when we come back, we're going to talk about why methicillin was originally great and why it doesn't work as well anymore. That'll be after Thanksgiving. If any of you are going to be in town for Thanksgiving and not going home because it's far or because you don't feel like it or because any reason, on Monday up at First Presbyterian Church, we're having a Friendsgiving where a lot of the faculty and staff are cooking Thanksgiving food, and it's really good food. And we would love any students to come up there that want to come up there Monday at noon. So if you're going to be in town, come up there Monday at noon. It's going to be a lot of turkey. A lot of good desserts and fun times. Have a great break.
There.
Yay! Are you really?
Yeah, really.
Good. I'm so glad.